All right, let's dive right into this. Welcome to today's explainer, where we're going deep into the functional safety strategies of high-voltage traction batteries. We are specifically zeroing in on the fourth dimension of these systems, the software, algorithm, and control logic layer. Today, we're decoding two absolutely critical fault codes for you, P1C5E and P0B26. These codes flag major state of health, or SOH, failures, and estimation performance anomalies. And trust me, we're not just talking about a loose wire or a bad cell here. So why on earth would a simple math error cause an EV to suddenly slash its power by 50%? Well, think of the battery as a patient, and the battery management system, the BMS, as the doctor trying to diagnose it. When physical anomalies severely twist the doctor's algorithms, the mathematical models totally fail to converge. When that happens, the system literally panics and triggers a massive safety response. Let's look at exactly how this unfolds. Here is our roadmap for the breakdown. We're covering 5 main phases. First, root cause analysis. Second, architecture and fail-safe mechanisms. Third, design prevention through DFMEA. Fourth, process control via PFMEA. And fifth, mass production validation. Starting off with Phase 1, root cause analysis, let's look at the physical and electrical origins of why this SOH divergence happens in the first place. Now, what's really interesting about this slide is how these failures are essentially math contradictions triggered by timing and power distortions. There are 2 main culprits here. On the left, we've got sync errors. During highly dynamic events, like when you just floor the accelerator, there's a tiny 10 to 50 millisecond polling delay between the main controller's voltage sampling and the chip checking the individual cells. When the current is massive, that tiny delay creates a huge virtual error in the math. On the right, we have the brownout. Imagine the BMS is writing critical aging data, and suddenly the 12-volt auxiliary power drops. That violent interruption completely wrecks the checksum and destroys the data structure. Let's move over to Phase 2 and see how this builds into the structural defenses inside the BMS, our architecture and fail-safe mechanisms. To prevent these math contradictions from just crashing the car, engineers use a brilliant defense called dual timescale decoupling. It's like separating oil and water. They isolate the state of health, the slow aging data, on a long lifetime scale. It might only update every few charge cycles or every 24 hours, keeping it totally safe from sudden, crazy voltage spikes. On the flip side, the state of charge, or SOC, lives on a highly dynamic timescale, so it can react instantly to high-frequency changes. They are deliberately isolating the slow aging metrics from the chaotic split-second driving dynamics. But what happens if the algorithm still detects an impossible massive jump in the data? The system triggers an extreme immune response. First, it instantly blocks any new memory writes, locking in the last known good data to prevent permanent corruption. Second, it enters a strict voltage fail-safe mode. Third, and you definitely feel this, it brutally derates the electric motor's power by 50% to protect the battery. Finally, it forces the vehicle into a low-speed limp mode. It is literally sacrificing performance to guarantee absolute safety. Moving right along to Phase 3, Design Prevention, or DFMEA. This is all about engineering out those critical Severity 7 risks before manufacturing even starts. In automotive engineering, suddenly losing power is a top-tier Severity 7 risk. To stop this, designers enforce incredibly strict countermeasures. They use an SOH fusion strategy, which is basically a multi-model algorithm that seamlessly swaps to a backup math model if one gets too noisy. They mandate 100% MISR-C software compliance to absolutely eliminate stuff like divide by zero errors. On the hardware side, it's pretty cool. They install a supercapacitor that provides a crucial 50 millisecond power buffer. If the 12-volt battery dies, this buys the system just enough time to save the data. Plus, they use dual bank flash memory, meaning there's always an automatic backup image ready to roll. Next up is Phase 4, Process Control, or PFMEA. How do we eliminate dangerous variations straight from the factory floor? So, the crucial point here is exactly that number, 100%. The quality control has to be flawless. Every single circuit board goes through 100% power dip testing on the assembly line. Engineers intentionally drop the voltage during memory writes to prove that backup supercapacitor actually works. There's a 100% end-of-line baseline write, hard-coding the precise chemical capacity from the battery plant into the BMS, so the math has a perfect starting point. And they run 100% 3D automated optical inspection on every tiny solder joint, making sure road vibrations won't sever communications a few years down the line. Finally, we reach Phase 5, Mass Production Validation, the DVP&R. This is the rigorous life cycle testing phase. Before any design gets the green light, it has to survive a simulated 10-year lifespan. Here's the timeline. Stage 1 tests the Extended Common Filter, or EKF, for algorithm accuracy. Stage 2 verifies the hardware sync. Stage 3 proves the system's auto-recovery. And Stage 4 tests the UDS aftermarket calibration. The absolute hard requirement here is that even after 800 brutal charge cycles, the software's estimation precision has to stay within a razor-thin 3.0% limit.
These validation tests are totally extreme. In Stage 1, the algorithm is tested without ever letting the battery fully charge, simulating the absolute worst user driving habits. In Stage 2, testers inject violent step currents of over 100 amps per millisecond. Why? To prove the new global hardware latch can synchronize voltage readings across the entire battery pack in under 1 microsecond. That blistering speed completely eliminates the old 50 millisecond delay we talked about in Phase 1, guaranteeing zero false alarms for the P0B26 code.
And the final stages are just as ruthless. They intentionally drop the 12-volt supply below 4.5 volts mid-operation. The system has to achieve a 100% auto-recovery rate by instantly grabbing uncorrupted data from the backup B partition. Finally, if a dealership swaps out the battery, the diagnostic tool gets exactly 500 milliseconds to wipe the old history. The vehicle then goes through one deep cycle and a 2-hour rest period to independently recalibrate itself back to that strict 2.0% precision. Which brings us to a really provocative thought to wrap things up. We've totally decoded the safety defenses behind these SOH fault codes. But to truly master these concepts, should we utilize Python to simulate these high-frequency step currents and actually visualize the algorithm's debouncing effectiveness? Just imagine how visualizing those sub-microsecond latch syncs could elevate your team's understanding of battery safety. Thanks for joining this explainer. Keep learning, keep questioning, and we'll see you next time.